Right. When Rudy asked me to do another evening with BSD a couple of months ago, I did some posts on various mailing lists asking for people to contribute to talk. I have been very busy and have not followed it too much, but haven't got much answer as well. So that left us with only one talk for tonight, FreeBSD 9. That's too short to fill the evening. So I was thinking, how can we fill the rest of the evening? Then I came across an email on one of the FreeBSD mailing lists. Someone saying, well, I've not been following what's going on for a while, and a lot of new stuff happens, and how do I now install my FreeBSD system? What should I use? Which file system, and partitioning and stuff like mirroring or RAID or whatever. There are so many choices what to choose from. That inspired me to write a talk on everything that pertains to installing your FreeBSD system and planning how to lay out your storage and use it. It involves bootloaders, partitioning, file systems, and the various GM modules for doing stuff like redundancy and other fun stuff. I should have thought of this a little bit earlier because there is quite a lot to tell about these subjects, and frankly it would be enough to fill a complete evening. But I already promised to do the FreeBSD 9 what's new, because FreeBSD 9 just came out. It's not something that you can postpone to the next BSD evening, and it will be old news. So we'll run over it quite quickly, but feel free to ask questions or grab me afterwards and discuss your views. I always start with a bit of history. Well, I like it. I looked up a little book, I should have bought it, called Unix the Book, written by Mr. Bannon and Mr. Rutter from the Instruction Set in London, printed 1982. My first reading on Unix. That's how I came to love Unix. And I've read the book until it fell apart. If you look at it, it's in a bookshelf now. All the pages are detached from the binding. I've read it over and over, but what I liked in Unix at that time is its simplicity. It's so elegant, simple, minimal, and still has everything you need to work with. And it was written in the times of, I think, 6th or 7th edition Bell Labs Unix. It describes the way a file system is laid out on disk, or the way your storage works. And in fact, this simple picture describes everything there is about how your disk is organized. The first block, that's dictated by the firmware of your computer, is usually the boot block. A block, by the way, is 512 bytes, half kilobyte. And what happens when you switch on your computer, there are some self-tests performed, and after that the firmware just copies the first block of your hard disk into memory at some address and then jumps to it in hopes that block contains code that will get your system to work for you. The second block was called the super block. The super block contains some pointers into the rest of what's on your disk. It told the operating system, once it's running, how large your disk is, how many blocks. It tells how many of these blocks are used to contain inode information, the file metadata. And it had a pointer to a list, linked list of 3 blocks. And it's got some statistics like how many blocks are in use at the moment. And it contained a flag whether the file system was considered clean or dirty. Once it gets mounted, the flag is set to dirty, and if you unmount it in a regular way, it's reset to clean. That was more or less what's important in the superblock. Then the inode blocks contained small data structures, 1 per file on your system. I believe there were something like 64 bytes in the beginning. They contained the size of a file, the type and the permission bits of the file, its last modification time, its last access time and last change time. 10 pointers to the first 10 blocks of that file on disk. 3 more pointers, 1 to an indirect block, 1 to a double indirect block, 1 to a triple. For further allocation, if your file is longer than 10 blocks, that's 5 kilobytes. Hardly ever see a file longer than that, still lower. Well, and behind your inode blocks there, the rest of the disk is data blocks. That's it. Very straightforward, very simple. Can be explained in 5 minutes. If you understand this, you understand how your machine works. We had big disk packs at that time. They hold something like 3 or 5 megabytes each. And it was very common that one disk was just one file system. If you needed more space than the 3 or 5 megabytes on your disk, then you needed a second disk drive with a disk pack, and then you mounted it on /USR, for instance. And just as simple as that. We all start simple. Babies are simple, but at some point of time we want stuff to be more sophisticated. We got bigger disks, and bigger, and even bigger, and well, it still continues to go. So there came a need to partition the data on your disk. Why would you partition your disk into virtual disks or partitions? One big reason is to protect applications from the misbehavior of other applications. If one application runs away and starts filling all the space on your disk, then at one point all your applications will stop because there is just not enough disk space anymore. By partitioning, you could make sure that even if your application runs away, you still can write log information about this to your log file system, so you know what happened. The first partitioning was done hard-coded in the driver. So there was a little C structure that you filled with the start and end points of each partition, then you compiled the driver again and kernel, and then you partitioned your disk effectively. I think you would not be very happy to do that nowadays. So BSD in the 70s came with something called the BSD label. And the BSD label is a data structure with a lot of information about your disk, and it also contained a table with 8 slots for 8 partitions. Well, 8 slots for 7 partitions. Slot A was generally used for the root file system, B was for your swap device if the disk contained swap space. Slot C was not really a partition, but it contained the well, the beginning was always block 0 and the end was the size of your disk. So the tool that maintains the BSD label would know how big your disk is. D was usually used for the dump partition, and then the last four, E to H, they could be used for your file systems like USR, var, home, and whatever you want. This is still the time of PDP and fax and control data and other large computers. In the 1980s, we got a new piece of equipment to play with, called the IBM PC with PC-DOS, which is later relabeled to MS-DOS or something like that. And a couple of years later, we got some new operating systems to choose from on that platform. IBM came with OS2 after they had a fight with Microsoft over the ownership of PC-DOS, that's why MS-DOS was split off. Xenix. Who started Xenix? Where's Xenix coming from? Any idea?
Microsoft.
Microsoft. Made they a big mistake letting Xenix go. Linux by Andrew Tenenbaum here in Amsterdam. A little bit later, Linux. And so people owning one of these very expensive pieces of equipment felt the need to be able to run MS-DOS today and Linux tonight or OS2 or whatever. So we needed multi-boot. Well, the answer to that was the MBR, the Master Boot Record, which was a little table that could divide your hard disk in your PC into 4 partitions. Well, 4 partitions pointed at by this table, and if you needed more, you could create extended partitions, which in fact is just a linked list. In the first block of one of the partitions, there was another MBR-like structure that pointed to the next partitioning. It's a linked list, so a lot of fun if you lose one of the blocks in this list, and you lose everything that's behind it. And the table contains the following pieces of data, some flags. Well, it was an 8-bit value of which they used one complete bit to tell which of the 4 is active. So out of 4 bytes, only 1 bit was used at the time. The start of your partition on the disk, but it was written in CHS, cylinder head sector notation. Because that's the way disk controllers at the time worked. You didn't address a particular block number on your disk, no, you said step 2, track number 45, and select head number 3, and then wait for the disk to rotate until sector number 4 passes the head and read or write it. And they all thought in CHS notation. There was a 1-byte type field, which would indicate whether this is a Linux or a Xenix or whatever operating system partition. The end of the partition, again in CHS notation, and later they used the last few bytes in that area for the start and the length of the partition, but now in a more sensible way. LBA stands for the logical block address, which is just a linear addressing, counting the sectors from 0 to whatever number of sectors is on the disk. But this is a table that we have had since the mid-80s, and that many systems nowadays are still using. This little table is stored in the first sector of your hard disk, the first sector of the first track under the first head of your disk. And a sector is 512 bytes. The last 2 bytes are filled with a magic value, 55AA, to indicate that this is really a boot sector. And then 4 slots of 16 bytes are taken off for this table. So that leaves 446 wall bytes to write your bootstrap loader. the piece of software that looks at the table to determine which of the partitions is active now and should be booted. Then find the right location on this disk and get the operating system from there. Format 46 byte is not much. Well, FreeBSD started, well, it was derived from 386 BSD, Bill showed it, but then FreeBSD itself started somewhere in the early 90s. And the old installer that we are about to abandon now gave you two choices, roughly. One was called the dangerously dedicated disk, which meant no partitioning whatsoever, a very simple bootloader in the first 512 bytes, no MBR, everything behind the first sector is just your disk to go with in the FreeBSD. Or install this master boot record that we just described, and one of the four partitions was then labeled for FreeBSD, type A5 in X or 165 decimal. In this partition we could make partitions the BSD way. Yeah, well, this is the beginning of a lot of confusion, because what's a partition? Is it one of the MBR partitions, or is it one of the BSD partitions? Well, BSD solved that by naming the MBR things slices instead of partitions. Partition was already in use as a name in BSD since the 70s, so I changed it.
Excuse me.
Yeah.
In Solaris, isn't it exactly the other way around?
Probably yes.
Slice 2 is your backup slice, and
That's correct.
the trailing slices in a F-disk partition.
And in SCO Unix, which died fortunately, it was partitions of the MBR and divisions inside. Yeah, this is one of the nice things that the world of PCs have brought us. World of confusion. Anyway, so you first divide your disk in up to 4 parts that can each contain an operating system, and the one containing your FreeBSD can then further be divided to have 7 partitions for FreeBSD. You could even use more than one MBR slice. I'll use the FreeBSD names now. More than one MBR slice to hold FreeBSD. If you need more than your 7 partitions, well, your boot partition, your swap partition, I like to have temp in a separate partition, and the VAR in a separate partition, USR, home, that's 6 already. If you need 1 or 2 more for your application, you're very quickly beyond the 7 partitions that the label allows, so I would just divide my disk roughly using the MBR first, and then put BSD labels in each of the MBR slices and have it to 28 partitions. What we said about the naming. The CHS model was limited originally to disks up to half a gigabyte, because you could have 1024 cylinders, 16 heads, and 63 sectors per platter. And if you multiply that together and then multiply it with 512 bytes, you end up with only half a gigabyte. Later they expanded this a little bit by allowing the head count to go up to 255. Can you imagine a disk with 255 heads? That means that you need 128 platters. It's never made. So we just fooled the device driver, make it believe that we have many heads, but the disk itself did some magic translation, and fortunately they never did it the same way twice. But we could go up to 8 gigabytes, which was in the early 90s something we hoped for but didn't want to wait for. We then had disks 512, 1 gigabyte, and that was a big disk already. The LBA address in the MBR table is 32 bits. We now don't use the CHS anymore, we only use the MBR and just forget about the CHS information. Nobody runs old operating systems that rely on the CHS information anymore. But 32-bit addresses and 512 bytes per block still stops counting at 2 terabytes. And I've already implemented lots of 2 terabyte disks, and the first 4 terabytes I believe are available or almost available now. So again, we hit a limit and we have to find a solution to that. The solution that Intel and a lot of other vendors in the PC world have been working on, and that's becoming the next standard, is called GPT, GUID partition table. It solves a lot of limitations and adds a few more benefits. It allows more partitions.
A quick question, 2 to the 32 times 512 is a lot more than 2 terabytes, I think.
2 to the 32nd is 4 gig. 4 gig times half K, to me that's 2 terabytes.
Oh yeah, no, you're right. I was off by
No problem.
10 to the 30. Or magnitude by between friends, no mind.
In fact, GPT, when you install it, can be told how many partitions you want, but the default is 128. You don't want 128 partitions on a disk, because then you have to plan in advance how large each partition is, so you're scattering your free space over up to 128 pieces of information, and after a short while you'll find out that one partition has more free space than needed and the other one is almost full. So you don't want them on the same way, but that's enough to play with. It switched to 64-bit LBA, which means we now have, no, it's not double, squared. An enormous maximum disk size. 2 to the 64th is in decimal something like a 1 with 19 zeros in that order. We got UUID, which is a unique, supposed to be unique identifier, worldwide unique, to define this disk. We were also faced with hardware vendors that do not agree on the order of bits in memory when I store something that's more than 1 byte in size, like an integer, whether we should put the lowest valued byte first or the most valued byte first. So if you move between PowerPC and Intel PCs, you always have to reverse the bytes in your integer to make them understood by the other hardware. This NDNS is built into GPT, so now both processors can understand the same disk. Not important, because the disk is in my machine and the processor is in my machine and I don't swap my processor. Or this is also a disk, and I can move it from this disk, which has an Intel CPU, to its predecessor, which has a PowerPC, which comes the other way around. Or a mobile hard disk that can be moved around between two architectures, a Sun with a Spark processor and a new Sun with an Intel, for instance. So this NDNS awareness in the partition table certainly has its value. And because this is such vital information, and I have seen too many disasters with machines where this particular block at the beginning of the disk was written to so often that the block was bad on the disk itself and you couldn't access all the other blocks because you lose your index. So decided that in GPT there are two copies of the GPT table, one at the beginning of the disk and one at the end of the disk. And if one of the two fails, you always have the backup at the other end. So this is replacing NVR now on modern hardware. All the Apple MacBooks are sold with GPT. They don't understand NVR altogether. And if you run machines with 2 terabyte disks or more than 2 terabyte, you do need GPT because NVR just doesn't cut it anymore. So that's another opportunity for accidents. Because now I got this new piece of, well, they call it a server, but to me it's still a PC. There's a GPT table on it. Now I put a CD in the drive or a DVD with another operating system that doesn't understand GPT. So it would consider the drive containing random data. It wouldn't warn you, if this was an install disk of an operating system, that the drive contains data in operating systems. It would just overwrite your disk. Well, I thought about that, and the first sector of your disk is filled with the PMBR, the protective master boot record, which just tells other operating systems, please don't touch it, the whole disk is taken by something called GPT. Okay, this is about the low-level partitioning. By the way, in GPT, each partition carries a identifier what's the kind of data inside the partition. The identifier is now a UUID, 128 bits instead of only 8 bits. And there are predefined values for FreeBSD. That's a FreeBSD label, so you can further make subpartitions in it. That is a FreeBSD swap area, a FreeBSD bootloader, or FreeBSD ZFS file system that you'll meet in a moment. About file systems. Well, the original file system in my little Unix book printed 1982 explained to me that the file system was divided in 512 blocks. There was one super block number 2 on the disk, or block number 1, which is the second block. There is only one inode table right behind the super block. All the 3 blocks are in a chain. So the first block is pointed at by the super block, and the first block points to the next. That's a typo, that should be 32-bit inode numbers. So you could only have, no, this is completely wrong, this is 16-bit. 16-bit inode numbers, should change it. 16-bit inode numbers, only 64K files. I remember in the 80s we were running servers with Usenet News, and they were hitting the 64K files per file system mark very quickly, so you had to dump all news quicker than you wanted, otherwise you couldn't get the new news in. Challenge already in the 80s. File names were limited to 14 characters because a directory was just a file under the hood with 16-byte fixed record length. 2 bytes were used for the inode number and 14 bytes for the file name, 0-padded. File names had to be ASCII names. Well, you could use high values, 128 to 255, but it's really dependent on your display what you would see. Collating sequence was just binary sorting, so internationalized characters that were often put in the high table of the character set did not sort properly into the alphabet, but we had a file system. Well, we got some improvements over the years, like in System 5 they changed the block size from 512 to 1K and later to 2K. Big deal, you would say. Well, remember the 10 pointers in your inode table that point to the first 10 blocks of your file. That means either a 5K file, a 10K file, or a 20K file that contains pointers directly in the inode. If your file grows bigger, you need an indirect block, which is one extra disk block, which points at the next number of blocks in your file. It makes a big difference if you hit the need for using an indirect block after 5K or 10K or 20K. Look at the FreeBSD source tree, count the number of files that are bigger than 5K but still smaller than 20. All these files on the original file system would at least need one extra block just to store pointers to everything beyond the first 5K. Growing the block size to 2K makes all files of 20K or less have only pointers in the inode block, no indirect block. So that made a big difference, both in space consumption and also in performance. Bad side of this was that you are losing, on average, half a K or 1K per file instead of 256 bytes. Because with large numbers of files, the last block is, by average, filled only half. Well, in the 3 megabyte per disk, 5 megabyte per disk time, this was an issue. This happened in the times that we had large disks, like 20 megabytes, and it was not that big an issue anymore. So we happily used bigger block sizes. And also the I/O was a little bit more efficient and faster. This was in System 5 world. In the fast file system, also called UFS in BSD world, they went even a bit further. We now have blocks and fragments, where a block is in fact 8 fragments, and large files are made out of blocks, except for the tail of the file, the last few bytes. If it's considerably less than a full block, it would just contain a few fragments. So the typical system had 4K block size and 512 byte fragments. And it was quite a bit more efficient, a lot less pointers, so a lot less indirect, double indirect, and triple indirect blocks on your file system. And because of the bigger block size, less scattering of data and faster I/O. They moved from a chain of 3 blocks to 3 block bitmaps, both in the System 5 world and in the fast file system in the BSD world. The BSD world added multiple copies of the superblock. So if one of the superblock copies, usually the first one, gets trashed, you can still access your file system and recover your data. Disks were getting bigger and bigger and bigger, and files more and more scattered over the disk, more fragmentation, and to counter that fragmentation they invented cylinder groups. So instead of having one inode table at the beginning of the disk and all the data blocks after, the disk was divided in areas of a certain number of cylinders, and each area had its own inode table, free bitmap and data blocks. And a sophisticated algorithm decided when you create a new file, if the directory where you create a file is in a cylinder group that is less than, I think, 80% full, the file is created in the same cylinder group. but if it's almost getting full, then the file is created in another cylinder group, and there are different numbers in percentages for creating files and creating subdirectories. And if one file grows, it originally grows in the same cylinder group until it reaches a certain size, and then it's forced to grow in another cylinder group, so that there is still some room left in the original cylinder group for small files that are growing. It's very sophisticated. It's, if you read the original paper by Bill Joy, it takes a lot of balancing, but in real world we see that many systems run with UFS or file systems that are derived from UFS, like the X2 and X3 file systems in the Linux world. And that worked for quite a while. We got variable length file names and 255 character limits on file names while growing, and some systems even implemented internationalized file names. UTF-8 is a very popular notation for that, or a very popular character set for that. But what we in fact did was take the original ID and tweak it, and tweak it again, and tweak it again, and put some more to it and some more. And, the file systems got bigger. It took longer to file system check after a crash, and to make sure that you can boot your machine quickly. We added journaling on some file systems, and that meant that you could instantly start your machine after a crash and then clean up automatically. FreeBSD got soft updates instead of journaling, which is not a very sophisticated system. It does ordered writes. After a crash, you can immediately start using your system, except that you may have lost some free blocks and inodes, but a background FSCK will find them for you and add them back to the system. Some file systems derived from the original file system change the directory format from a linear table to indexed structures like B trees for faster access and automatic sorting, and maybe there are even more, well, I'm sure there are even more improvements that have been made to this file system. But the bottom line is, this is all a file system that started in the early 70s. So we're talking about IDs that are 40 years old. We've enhanced them, but there comes a time when you have to stop enhancing what you've got and think about something new. Well, that's what Sun did, about 10 years ago, I guess. They invented ZFS, the zettabyte file system. It's written from scratch, and the way it works internally is more like a memory allocator than a traditional file system. It has many interesting new features. One thing is that data is never overwritten in place, but everything is copied on write. And because all the data is structured in tree-like structures on the disk, you start writing your changes from the leaves up, so your data blocks or your inode information, and then you work your way up the tree. And at the top of the tree is something, well, they call it the Uber block, which is like the super block in traditional file systems. When finally this Uber block is pointed to the new top of the tree, and your system crashes and it comes up, you get all your data. If, however, between starting with your leaves and working your way up, you have not yet reached the top of the tree and your system crashes, then after a reboot, it starts looking from the top of the tree, it sees the old state before the last changes, so you've lost some of your data, but your file system is stable. And no matter how big your file system, you can immediately start running your system. You don't have the file system change. I've read these stories on the FreeBSD mailing list. UFS file systems like 6, 8, 10 terabytes with millions and millions of files. FSCK stops after 6 days because it runs out of memory, because the machine only has 8 gigabytes of memory. That's quite frustrating if you have been down for 6 days already and FSCK doesn't finish. So having a file system which is always clean by design, even if you lose the last few writes to your disk, but it's still much better than a system that's not available for a long time because you have to recover after a crash. Well, about sizes of stuff, we've always been fighting decisions of, well, let's make it 16 bits because that's once in the past was the natural size for integers on the machine, and later we made it 32 bits, but we always reach the end of capacity before you like it, because 16, 32 bits just doesn't cut it. Sun said, well, we don't go for 64, we just go for 128. 128 bits, it's the same number as bits in the IPv6 address. It's totally enough to give a unique address to every single atom in the universe. Maybe a few bits off, but we're very close. So chances that we need more than 128 bits less, I never say never, but I don't think we will not be there when we hit the limit. ZFS, and that's when I first heard about it, completely against my idea of clean programming and coding, where you want to layer stuff. ZFS now combines the file system and volume management, both volume management and stuff like mirroring and weight or redundancy stuff. I've been using ZFS since 2007, I think, so that's about 5 years now. Yes, I like separation in layers, but I see that with ZFS it's very nice that it's in one system together, because the layers work together very well, and I'm not sure whether you could reach that efficiency if you do strict layering. So it has built-in volume management stuff, mirroring and RAID C with 1, 2, or 3 parity disk. RAID C works a bit like RAID 5, but has some very good points beyond RAID 5. It also has a concept of storage pools. You combine one or more disks into a storage pool, and you create file systems out of the storage pool, but they all share the same space in the pool. So if you just install ZFS the first time and you create 3 or 4 file systems, let's say you have got 4 disks of 2 terabytes and you're mirroring them 2 by 2 and then striping them. So your net capacity is 4 terabytes. Type DF, and you see that all your file systems have 4 terabytes. If you start writing files in one of the file systems, the free space in all the file systems goes down. You want to protect applications from runaways on other file systems, like I said when we talked about partitioning. You can do that in ZFS by putting a quota on a file system. You just say, well, /var can grow up to 8 gigabytes. And /USR only needs 4 gigabytes because it's the FreeBSD stuff and a handful of ports. And I give 16 gigabytes to /home. And typing df then shows you the available space, taking into account the quota you have put on your file system. Now your file system gets almost full, and I need more space in home. In the old days, I have to change my partitioning. Find a bigger partition for home. Or do kind of tricks by putting a little layer in between that would concatenate two partitions, maybe on two different disks, into one virtual partition, and then grow your file system. After drinking too much, I still have nightmares about machines that I have had to change because file systems went full. In ZFS, you just change your quota. It's one command line you type, and instantly the file system gets the extra space. Or you can shrink a file system. If this heavy user that's taking up much of your home leaves your system because it gets its own system, or even leaves the company, then you can just go /home back from 16 gigs to 8 gigs if you want to. There's much more to it. Reservations, which is just the opposite. You reserve some space for a file system. It can go beyond that, but it at least has that amount of space available. And there's much more. It's too much to tell in one evening. Another thing is that everything that's written to the disk is checksummed. And the checksum is written up the tree one level. So the checksum is never in the same place as the data that is being checksummed. This means that when your hardware fails, and after reading a piece of data from the disk, you get a different piece of data than you've written to it in the past, the checksum will tell the operating system that the data has changed. And ZFS is self-healing, meaning that it will detect that the checksum is not correct. If your disk is mirrored, and now it becomes very handy that the volume management and the file system are integrated, it knows where to fix the other copy on the other disk. So if the disk is at fault, it will find the other copy on the other disk and say, hey, this checksum is correct, so I can use it. And at the same time, it writes it back to the bedrock. So if your disk is getting weak, it can happen that you read back data and the checksum of your hard disk, which is in the intersector area, does not reveal the problem, but ZFS detects the problem, then your block is written back. If during write your disk sees a write error, modern disks will automatically remap that sector, so you get a brand new sector with a copy, the good copy, which is taken from the mirror of your disk. Compare this to traditional systems with RAID controllers or software RAID systems or firmware-based, as is very popular in PC world now. If one disk goes bad, well, if one sector is bad, the disk is flagged bad and not used anymore. You as an operator have to intervene and recover it in some way. ZFS will do that for you on the fly, and type zpool status, and it will show you how many repairs it has done, so you always know the health of your system. ZFS is good at snapshots. In fact, as I said, it's doing copy on write for everything that you write to your disk. And normally, after the changes went up to the top of the tree, then the old data which is below that is considered free space again. So it's added to another tree-like structure that points at all the free space. When you create a snapshot, the old data below is still referenced by the snapshot, so it's not freed as long as the snapshot exists. It's something that's very natural to go with this copy on write system. And creating a snapshot is really a fast operation. Snapshots by nature are read-only. When you create a snapshot, it's like a frozen image at that point of time of your file system. Clones can be taken from a snapshot. A snapshot can be promoted to a clone, which means that it becomes writable again and starts a life of its own. ZVols are volumes. It's an amount of storage that is not presented as a file. Internally it works exactly like a file, but it's presented as a block device. Compare this to the old way of doing on UFS file systems. You would have to create a file and then use mdconfig, or in the old days vmconfig, to make a new virtual block device out of it, and you can use it for stuff like swap space or mounting file systems and stuff like that. ZVols is something at the file system layer that you can create something with a name like a file system, but it's in fact a block device in which you can do other stuff. Also used by some high-end databases like Oracle and other databases, like to have raw partitions. This is the counterpart of raw partitions. It takes a little while to get used to the ease of creating snapshots and the real power that's unleashed by this cheap way of snapshotting. You can do all kinds of very neat things with it. On my customer file systems, like home and data and whatever file systems that people write to, I run a cron job that creates a snapshot every 5 minutes of every file system. And another cron job destroys the snapshots after 3 hours, except for the snapshots made on the hour. They are kept for another couple of days, except for the snapshot made midnight, which is kept for a month and a half. And snapshots are instantly visible as a hidden subdirectory under the mount point. So if someone accidentally removes or overwrites an important file and they call me and say, hey Paul, I just lost this file, or I just overwrote my file, or usually it's someone else who did this, I just tell them, well, type this path and it brings you back to the copy of 5 minutes ago. Or if you did this just before lunch and discovered it right now after lunch, go back to this path and you get it like it was at 11:45 or whatever time you think your data was still intact. And because snapshots are so cheap, cheap in terms of time that it takes to create them, and cheap in terms of storage that it needs, well, a snapshot does not need extra space until you start changing your data above the snapshot. Then the changes take space. The snapshot itself, when you take it, takes no more space. It's just one extra pointer, one extra reference, that's all. File systems can be divided further into sub-file systems. So my /home is divided in /home/Paul and /home/ whatever user is on the system. This comes very handy. Well, I told you about the quota. I can put a quota of 16 gigabytes on /home and then give every user on the system a quota of 2 gigabytes, even if I have 15 users. That means that every individual user cannot use more than 2 gigabytes under their home directory, and they all together can take it to 16. Quota is what they call a property of a file system. A file system has many properties. Some of them are just read-only statistics about the file system. Others can be tuned to change the behavior. A very popular one is compression. I can set compression equals on a file system, and then it automatically compresses all data that I write to the file system from that time on. And properties inherit to sub-file systems. So if I switch compression on /home, then all the subdirectories below are automatically compressed. Unless I explicitly switch it off on one of them, that's possible too. Well, compression, quota, reservation, and so on. Deduplication, well, explained to you before in the talk before the break. Another very nice feature about CFS is the send-receive system. Send is a subcommand of CFS that creates a stream that represents everything which is in a file system from the beginning up to a certain snapshot. Or everything that has changed between one snapshot and another one. And receive can consume such a stream of data and recreate a file system out of it. And this is a very neat way of replicating a file system from one machine to another one. With ZFS send, you create a stream from the beginning to your first snapshot on machine A, you receive it on machine B, and you get the same file system back up to that snapshot. With the incremental version, where you go from snapshot A to snapshot B, and you copy it from one machine to the other one, you incrementally add everything that is changed between snapshot A and B on the other machine. It can even do a send from, like say, the first snapshot and the 20th snapshot, preserving every snapshot in between. So your replica contains every snapshot in between as well. Very powerful. Well, much more about CFS, but we go on. You fill a complete evening on that.
Sorry, Paul.
Yep.
Does it also support encryption?
ZFS version 28, as we have it in FreeBSD 8 stable, 8.3 and 9 at the moment, does not incorporate encryption. I know that there were plans at Sun to add encryption after 28. I believe it's still...
Solaris Express has it. Open Solaris.
Yeah, I think it's in 31 or so.
Yeah, I use it right now.
Yeah. So it was on the roadmap. As I said, ZFS Live after Sunset, Sun is bought by Oracle, and Oracle has different plans than Sun had. We do not exactly know what will happen. ZFS itself was distributed or released under the CDDL license, which is a license which is more open than the GNU license. It's in a certain way compatible to the BSD license. We can use CDDL stuff under certain restrictions together with BSD license operating systems. But what will happen to the future of ZFS is not really clear. There are some derived projects like the Illumos and the Open Indiana projects that continue the inheritance of Sun, the Open Solaris operating system, to the future. I know that there is a group of people with interest in what's happening here, who have stakes in various operating systems that work with ZFS, who are talking about the future and working towards something usable, but they have decided that this will happen behind closed doors for a while, and we don't know what's happening behind those doors at the moment, but I'm convinced that something will come out of it and that there will be a future after version 28. Whether that will be in line with what's going on with Oracle or whether it will be a fork is to be seen.
Just a question. How many of the ZFS engineers are still at Oracle?
I don't know exact numbers. I know that some of them left.
Many of them have left.
Yeah, less than that.
I don't think Oracle is really interested in putting much efforts in innovating ZFS right now.
At one point in time I was afraid that Oracle would degrade OpenSolaris to a bootstrap loader for the Oracle database.
Yeah, something like that. Yeah.
The truth will be somewhere between the original Sun plans and this extreme view, but I think for most people in this room the takeover of Sun by Oracle is not really beneficial. So, well, ZFS was ported to FreeBSD. This started somewhere in 2006, only 2 years after Sun officially announced and released ZFS the first time. We started with a very old version, I think version 5 or so of the ZFS in FreeBSD.
It's 5, yeah.
It was quite unstable. I ran it on a couple of test machines at that time just to see what ZFS is all about, and I really liked the power of it, and I was sure this, when it matures, is the way to go. No more static partitioning of your hard disk, all the planning, how much do I take for var and how much for temp and how much for USR and how much for home, and nightmares. So ZFS, well, we have been using version 14 until 2 years ago, version 15 until FreeBSD 8.2. Skipped from 15 to 28, FreeBSD 8.3 and 9.0. I have been using ZFS in production on dozens of machines, including customer machines, for the last 2.5 years now. It's rock solid and always works. And, the biggest problem is me getting used to all the new features and make the best use of it. There are some negative sides in terms of the performance behavior. The copy on write has a penalty. Many other mechanisms like combining writes into bursts once every 30 seconds or whatever you specify makes up a bit for the performance difference. Having multiple levels of caching, you can have, well, there's always a memory cache, but on top of that you can do caching on a fast device like an SSD. Makes up a lot, but there are still circumstances, usage patterns of your machine where the performance is not what you are used to with other file systems. In other cases it's even much better. It's a different beast. It's completely new compared to old file systems, and it takes the average sysadmin a couple of years to really get acquainted to it and know all the ins and outs and know how to best put it to use.
Do you mind if I comment on that? I've been using it, let's say, since 2007 in Solaris, and it requires quite a bit of memory.
Yeah.
It's very memory intensive.
Yeah.
That's very important if you start using ZFS. Just make sure you got lots of RAM.
I should have put this into the slides. ZFS is memory hungry. Consensus in the FreeBSD project is don't run ZFS on a machine with less than 4 gigs of memory. But ZFS also loves large address space. If you don't have more than 4 gigs of physical memory, you still need a 64-bit operating system to make it really this stable. It runs in 32-bit mode as well, but under heavy pressure it can run out of address space, even if it's not running out of physical memory, but it's just running out of address space, and that's not good for the stability of your system. So don't run this on your 32-bit server, and don't run it with less the 4 gigs of memory.
I've tried both.
Sorry?
I've tried both. It really crashes.
Yeah.
Yeah.
Well, I still know ways to crash it on an 8 or 24 gig machine with 64-bit addressing as well. But I also know how to make it not crash. ZFS is also available in the Linux world, but only in user and in a few, because of the licensing. The new license, as I said before, is contagious, and the CDDL license just prevents it to be included in an operating system which is released under the GNU license. The Linux world is working on a new file system called Btrfs, which shares a lot of the IDs of ZFS, but written from scratch. I don't know how long they've been working on Btrfs so far, but I guess ZFS is much more mature at the moment. I don't know if Btrfs is out already, but
it's not stable yet, but I believe that OpenSUSE is implementing it as default in the upcoming release. So it's not officially stable, but a lot of developers think it is. So
okay.
Yeah.
Thank you. I'm not a Linux user, so I can just take your comment and relay it here. The Dragonfly people have been working on HammerFS for a while now. Magellan mostly is doing that. HammerFS is also a completely new file system with some of the IDs which are quite parallel to the ZFS IDs. I've not used it. I'd really like to have a talk on HammerFS one day, but it's very difficult to get hold of the Dragonfly people. They're very much on their own.
I have one more question about ZFS. The last time I worked with it, there were some issues on getting it bootable. Is ZFS bootable at this?
You're talking FreeBSD?
Yeah.
It's perfectly bootable. We'll come to that in a moment.
Okay.
Well, bootstrap loaders. The original FreeBSD, as I said before, had 2 modes of installation, dangerously dedicated or with an MBR. So when you boot your machine, the typical sequence is the power on self-test done by the firmware or BIOS in your machine. The stage, I call it IPL, like in the old days, the initial program load, which means copy the first sector of your hard disk into memory and jump to it. That first sector contains either MBR, which is a bootloader that comes with FreeBSD, which just takes the partition that's marked active at that moment and starts it, or boot 0, which is a bootloader that looks at the partitions that are available on your machine, prints a little menu at the top of your screen, waits for input whether you want to start 1, 2, 3 or 4 in your MBR table, and then boots it. What it then does is either the MBR or the boot 0 take the first sector within that partition, load that into memory and jump to it. So it's more or less chaining the boot process to the next stage, which is called boot 1. It's also a 512 byte sector, so it cannot be large, it cannot hold enough code to understand file systems. So what boot 1 does is copy the next 15 sectors or 7.5K beyond boot 1 in memory and jump to it. That's called boot 2. Boot 2 being 7.5K has just enough knowledge about file systems like UFS to find the next stage, which is called loader, and loader is actually the file in the stage boot directory on your FreeBSD machine. Loader is a standalone executable, meaning it does not need a Unix kernel to run. It's linked to a library that gives some basic I/O capabilities, but is quite limited compared to the kernel, but enough to go on. And loader has a built-in programming language, which is called Fickle, Forth-inspired command language. Forth is a very minimal stack-oriented language. Loader has enough understanding of your file system and can look at all kinds of information on your machine and do stuff like load the kernel, load additional modules, set some kernel variables like how much kernel address space do you want, and other stuff that you cannot choose once the kernel has started. And then after loading the kernel, setting all the parameters and loading the modules, it jumps to the kernel and the kernel does the work. So in fact we have, well, post is not part of the boot process, it's just checking the hardware. IPL, the first level boot, the second level boot, the third level boot, the loader, the kernel. The kernel is the 6th program in a row that starts. Yeah. This is innovation, but in a way I don't like. Why not put a little marker at the end of the first sector that tells the IPL how many sectors to load and to start? Would make life so much easier, but nobody never thought about it. And now we're stuck with de facto standards. Well, the MBR always use the active license boot 0 as a menu. Just told you about that. There are new bootloaders called GPT boot and GPT ZFS boot. Boot 0 and MBR just know about the MBR table. They don't understand the more complex GPT tables. So that's why we have new bootloaders called GPT boot and GPT ZFS boot. GPT boot knows about the GPT partition tables and knows about the UFS file system to find loader and kernel. GPT ZFS boot, as the name suggests, is the same, but instead of UFS it understands ZFS enough to load your kernel, or your loader, sorry, to load your loader, and the loader then loads the kernel. These new boot loaders don't have the selection menu as we had in boot 0 anymore. So with boot 0 you can install 2 or 3, 4 operating systems on the machine, and then at boot time select which of the 2, 3 or 4 operating systems will be started. The 2 new loaders, GPT boot and GPT ZFS boot, don't have that feature anymore. There is one new feature, however, and that's a kind of, well, called a try once option, which means assume that in slice 1 or partition 1 in GPT I have my system that has been running for a while, that's stable, and I just installed a new version in partition 2 and I want to try it. I leave partition 1, the active partition, but I put a try once bit on the second partition. That means that GPT boot or GPT ZFS boot will boot from the second partition, but before booting from the second partition it will clear this try once flag. That means that if the boot succeeds, I'm running from partition 2, which is my new partition, and I can use a command in the operating system to change the active from partition 1 to partition 2. If the boot fails, I just have to make sure that the machine gets a reset, push, or power cycled, and then I'm back at partition 1, because that one is the active one, and there is no try once bit after the first try. So this is very handy when my machine is miles away in a data center, maybe across the world, 20,000 kilometers from here in Sydney or whatever. Worst case, I have to phone up the ISP and ask them to push the power or the reset button. but I know that after one failed try, it falls back to the known to work partition. Maybe it's even better than the boot 0, which has a menu on the screen, because then you need a screen and a keyboard. And machines in a regular data center don't have a keyboard and a screen attached. And depending on your hardware, you either need a VGA screen and either a PS2 or a USB keyboard, or maybe even a SEM keyboard. Or you have a machine with a serial console, and then you need someone who has a PC with a terminal emulator and a serial port and knows how to use it. And this try once option, well, you just need someone who knows where to find the reset button or the power button and press it. But it's different. We get new stuff and we lose some old.
Especially in data center, you often have a remote control for the power button.
Depends on your ISPs.
You don't have a console. That's a quick option.
Some ISPs provide a remote power cycle, remote reset, do it yourself, and some don't, and then you have to call them and they'll do it for you. It just depends on your ISP. Yeah. Well, I'm talking ISPs now. It can also be your own data center if you're working for a large company and you've got remote data centers. The last bootloader, I'm not going to tell a lot about it. It's called Grub, or there's now Grub version 2. Grub originally was derived from the FreeBSD bootloader. It tries to do away with all the different bootloaders by all the different operating systems, because we have now been talking about the FreeBSD bootloader, but if I want to multi-boot with different operating systems, the question is always which of the bootloaders do I use, because every operating system has a different bootloader. I have dual booted machines. Well, I have to confess, in the past I have installed machines for people with both a Microsoft-based operating system and FreeBSD. I use boot 0 because it can equally well boot the Microsoft system and FreeBSD. I have done a lot of machines with FreeBSD and, for instance, OpenSolaris or NetBSD or OpenBSD on it. And boot 0 knows about it all and works quite well. But it's always a question, what bootloader do you want? And the guy who wrote Grub, I said, I now want a operating system independent bootloader that understands it all and is extensible and has a nice user-friendly manual. It's in ports, you can install it from ports, it works. I don't use it myself that much, except on machines where it's preloaded with the operating system of OpenSolaris. Right. The other thing I promised is Geom. Geom is a framework that was introduced into FreeBSD 5 by Paul Hennekamp, which creates an abstraction for block devices. Block devices originally in Unix was a classification. Devices came in two types, block and character devices, and the difference was the API in the kernel, the type of operations that the device supported, the device driver supported. FreeBSD has done with block devices for a long time. We only have character devices in FreeBSD. When I talk about the block device in this talk, I just mean some kind of storage that is addressed in blocks of data, typically 512 bytes, or nowadays we also have disks with larger block sizes, but anything that can be used as a storage to hold data. The Geom framework supports Geom classes. A class is a piece of code, a module in your kernel that performs a certain task, like mirroring 2 disks or implementation of a RAID 5 or putting a cache layer in between a disk and the file system. Every time when I use this class, I create an instance for that. It's not too surprising. 2 important terms in the Geom language are providers and consumers. Every Geom instance consumes 1 or more block devices at the bottom and provides 1 or more block devices on the top. And I've symbolized that with little triangles, the black one pointing up and the white one pointing down. Going from top to bottom, if I've got two visible disks, the disk driver will provide 2 entries in the /dev directory. I'm using the HCI driver, so I get ADA0 and ADA1 if they're SATA disks, or at FreeBSD 9 if they're IDE disks as well. So there are 2 names, 2 providers in the /dev directory. I instantiate the mirror class, and this mirror class consumes at the bottom 1 or more disks. I can make a mirror of a single disk, which is in fact not a mirror, but it can exist. It can have 2, it can also have 3 or 4 replicas of the same. And at the top it provides a new name under /dev, /dev/mirror in this case. And the name is given when I create this instance. I call it Geom0, Geom mirror number 0. And I put the next layer on top of it, and this is a Geom layer partitioner for a BSD label. The partition table that has 8 slots that we saw in the past before install. And this one provides 7 more names on top. Partition A, B, D, E, F, G, and H. Remember, C was the whole disk, or in this case the whole consumer below it. And so I can stack layers on top of each other. And I can squeeze another layer in between that does encryption or caching, or another nifty module is Geom Gate. Geom Gate is a very typical, very specific one because it comes in 2 halves. The gate daemon and the gate client. One is only a provider, the other is only a consumer. I attach the consumer to some device on one machine. I start a provider on the other machine. They communicate through the network, and this way I can have a block device on one machine accessing a physical disk on another one. Very nice. So I can do mirroring cross network. And this modernization is very powerful because the interface, the API between the layers is always the same. So if I can dream up something I can do with storage, and I can express it in a way that it consumes data block by block, and it provides data in another way, I can just insert it at every place. It's up to the sysadmin how to best use what I've written in real life. And we'll see a list of Geoms that are available in FreeBSD 9 in a moment. The way it works is when hardware is detected, the hardware device driver creates an entry in the /dev directory. This is done during boot time for all the disks that are available in your machine, but it's also done, for instance, when I plug in a memory stick into my USB port. The USB subsystem will detect my memory stick. So my memory stick as a storage device, and present it as a disk, as a DA, a SCSI attached disk, because USB sticks are using the SCSI protocol. And once a name is created in the /dev directory, all the geom classes are called one after the other and asked, do you like this device? Do you think you can use it? That is called the tasting of the device. And these geom layers usually put a block of metadata somewhere on the provider, on the layer below, to tell what it is and how it's configured. So for instance, geom mirror, they usually use the last sector of the disk or the device below. Geom mirror will write in the last sector of ADA0 and ADA1 that it's a mirror. It'll have a unique identifier that if both have the same identifier, it means they are two disks of the same mirror. They have a sequence number. So the first one I add to the mirror is called number 0, the second one is number 1, and so on. And when this disk appears, all the geom classes are called for tasting. And for instance, if I've got a geom, well, let's say this one, if this one is offered this provider, it says, well, no, this is not my metadata yet. And then the mirror at one moment is called and it says, hey, this is my metadata. This metadata says it's a mirror. And what it does is it creates this instance. It provides a copy of this block device here, except for the last sector, because that's its metadata. So if my if this disk would be 1000 blocks, geom0 is 999 blocks long. And geom mirror, when it is first tasted, when the first disk appears, it knows that the mirror is incomplete. So what it will do is it will schedule a timer in the kernel. It will not yet provide the geom0. It will wait a certain time for the rest of the mirror to appear. So during the boot, all the disks are found one by one by the SATA driver. And once they are found, they are created in the dev directory and the geom layers are called. And geom mirror finds the first one. Hey, this is part of a mirror. Let's schedule a timer to wait for more of the mirror to appear. In the meantime, the kernel will find the second disk. They'll call the geom mirror again. Geom mirror says, hey, this is also part of the mirror, and already have the other half. Connect them together, create the geom0 instance. Once the geom0 instance is created, the geom0 provider is created, which is named /dev, the same process happens again. All the geom layers are called one by one. And if this one happens to have the BSD label in it, then at one point the partition BSD class says, hey, I recognize this as a BSD label, so I'll take this one and I'll provide the 7 layers on top. And now it's very feasible, if you want, to turn around to put a BSD label on this one, and put a BSD label on this one. So on top of the BSD layer I'll have ADA0A, and here I'll have ADA1A, and then I can put a mirror on top of ADA0A and 1A. So instead of mirroring the disk below the BSD label, I can also take 2 partitions that are inside the BSD label and mirror them. And it's up to your imagination how you combine the stuff. It's much like Lego. Every provider does rough counting. It knows how many consumers are using this provider at the moment. This is a one-to-one relationship that I could open the same device in the /dev directory by a PRO run and the rough count goes up. Sometimes geom layers do stuff that requires multiple access to the same bottom layer, no problem. Once the ref count is non-zero, the device is in use. And if, for some reason, I overwrite this metadata, then, for instance, on a running system, I change my MBR partition table with a column called fdisk, or its newer counterpart called gpart, then the driver knows, hey, something has changed. And what it does is a process called spoiling. It will say, this is no longer valid. Go away and decide to retaste. So also if I clear the last block of my mirror, the metadata that tells that ADA0 is part of a mirror, it's spoiled. So this connection is broken. A new round of tasting, but because the metadata is not there anymore, GeoMirror will not consume it. And you have to get used to it, but it's, well, once you work with it, it's very natural, it's mostly behind the scenes, but it's a very powerful mechanism. Sometimes leading to unexpected stuff. As a sysadmin, you have to be aware. For example, I've got two servers. They both have a bunch of drives, and I've both put, well, either a RAID 3 or a RAID 5 on it, or maybe RAID Z with CFS. One machine breaks down. It takes a day to repair, but I need my data. If I'm able to connect the drives of this machine to the other one, and it happens to have GM classes with the same name as the other machine, it's getting confused. Yeah, so if I've got two machines with two disks and they both have a GM0, and I connect the drives of one machine to the other one that already has a GM0, it says, hey, more disks with GM0, this doesn't fit. You could solve that easily by calling GM0 on one machine and GM1 on the other machine, or call it dog on one machine and cat on the other, or whatever name you want to give, because GM0 is just a name I made up. But the automatic tasting, if I plug a drive into a machine, or if I boot a machine with a drive plugged in, it's necessary for the GM framework to work, but you have to be aware as a sysadmin. Let's see, how far are we? Oh, the GM modules, I promised. Now, there are several partitioning layers, MBR, GPT, BSD. There's another one for System 5 VTalk. There's one for the Sun label. There's one for the Apple partition table. There's one for, I think it's called EBR on the PC98 platform, which is the Japanese version of the PC. GM concat, which is just the ordinary concatenation. You take two providers and you take two consumers, they're combined into one new provider that is the size of the sum of both minus the two meta blocks. A stripe, which does the interleaving for you. Mirror, we just discussed it. RAID 3. RAID 3 is well, it's similar to RAID 5 but not the same. RAID 5 can take any number of disks, use n-1 disks for data and stores a parity on disk n, but the parity rotates from stripe to stripe. RAID 3 does something different. It takes one sector of, well, it can be done with the number of disks in the RAID 3 has to be a power of 2 plus 1. So 3 or 5 or 9 or 17. With 3 drives, the sectors of the parallel sectors of the both data drives are combined as a supersector, so I get a sector size of 1K, and the parity of that is written into a third drive. The advantage of using RAID 3 over RAID 5 is that with RAID 5 there is a lot of logistics if whatever I write is not a full stripe. If I write one block in a stripe, assume the stripe is 4 plus parity drives, then the operating system has to read 3 other blocks in the stripe, calculate the parity and write back 5 blocks to just change one. So 3 reads plus 5 writes is 1 block write in RAID 5. RAID 3, because it always creates new sector sizes at the top, either 2 or 4 or 8 times the original sector size. All the writes of the file system are forced to be in a new sector size, 1K, 2K, 4K, and this means there is never this this write gap of having to read part of the data to reconstruct the parity of the rest of it. BDE is an experimental encryption layer, just a proof of concept, don't use it, it's still there. ELI is a production quality encryption layer. UZIP does on-the-fly decompression of zip compressed, gzip compressed file systems. Nice for embedded devices where you have only little flash space available. You compress your file system, put it in a partition, and include UZIP in your kernel, and then recognize the compressed file system and present it as a non-compressed file system at the top. Cache, talk about it. Journal is a generic journaling layer that is operating system agnostic. So it doesn't. So it's a file system agnostic. It doesn't know what file system is on top. It just prevents a journal for whatever you write to your block device. Competa I just explained to you for the split of a daemon and a client on 2 machines. The physical block device is on 1 machine, but the access is through a dev entry on the other machine. Multipathing, I told you before already, if there are multiple physical connections between your disk and your system. Fox is another multipathing driver with other characteristics. Many file systems have the ability to have a file system label in the first block of the file system, or super block, or little block, whatever you want to call it. GM label is a generic label layer where you can just give a label to a block device. And sometimes it's handy not to use the file system label, but for instance, if you want to have one label to cover all the partitions of a BSD labeled file system, you can use this. GeoNoc is a transparent layer that just gives you on the top whatever is red on the bottom, but it has some very nice parameters. For instance, you can tune it to simulate some error rate. So if you're developing layers on top where you have to recover from disk failures, you can put a GeoNoc in between and tell GeoNoc that it must produce a read error once every 1000 reads, or a write error once every 1000 writes, or whatever rate you want. Another thing that GeoNoc can do is you can present your same block device with a different sector size on top. And that comes in very handy nowadays because disk manufacturers are slowly moving from 512 byte sectors to 4K sectors, so you can cram even more data on the hard disks. If your file system thinks that your data is written in 512 byte blocks, and your disk is 4K sector size, and your file system just writes a couple of blocks, which is not a multiple of 4K at a 4K boundary, then the controller which is on your disk has to do all kind of magic by reading the remaining parts, filling in the part that you've changed and writing it back, much like the problem with RAID 5 I just described. And that costs you a lot of performance. Since we still live and think in a 512 byte per sector world, the default when you install a system is that partitions and everything is on 512 byte boundaries. If that does not coincide with the 4K boundary, you have no performance left. So if I want to install my machine future-proof, I now have disks which are 512 bytes per sector, but I may change them in the future with new disks that are 4K. Then I can put a NOP layer on top of my physical disk and tell the NOP layer to present 4K sectors on the top. And then create my file systems and everything in a 4K sector world. Then I can take the NOP layer out. For instance, CFS, when creating a pool, it detects the sector size, it stores it in the metadata of the pool, and it doesn't change it afterwards. So if I replace a disk in an existing pool, it doesn't change the sector size. If it knows that the sector size is 4K when I create a pool, then it will always be 4K and nicely aligned with the 4K sectors of my physical disk if I change it in the future. GeoVerStore. Some people earn a little bit of money and still want to buy expensive stuff. They borrow. VerStore is something similar. I create a 16 petabyte file system on top of my 2 terabyte disk with VerStore. I just say, give me a provider that is 16 petabytes and add my 2 terabyte disk as a consumer on the bottom. It keeps track of the blocks that I write to my virtual large disk on top, maps them to physical blocks on the bottom as I write, and I can just use the raw address space of the 16 petabytes. My file system, if it's UFS, it'll work in cylinder group, so it will not start writing from the beginning. It will write here and there and there and there. GeoVerStore just uses the underlying disk, well, more or less sequentially, has a little map in the front, and it knows how much of my physical disk is used. So I can ask that, like, check it every week, or with my Nagios or whatever, check it and give me an alarm if it reaches 80%. And once it reaches 80%, I stuff another disk in the machine and I say add it to the VerStore. So I can start with small disks, present a large file system on top, and gradually add more disks as I go. Personally, I prefer ZFS. In ZFS, I create a pool out of my disks. I can later add disks to my pool, and when I add this to my pool, the space in my pool grows instantly. I can even replace one by one my existing disks by bigger ones. So they are copied from the old to the new disks. Assuming I have a machine with 5 1 terabyte disks, one by one I replace them by a 2 terabyte disk. After I replace the last one, my net storage capacity doubles instantly.
You need an export and import.
You had to do that in the past. I believe there's now a
online
pool.
You have this auto-expand feature that you can enable on the pool. That's only the most recent versions.
Yeah, but we're talking since the talk before the break. We're now only talking FreeBSD 9 and above. Everything before.
Old stuff.
And CFS allows you to do a similar thing to VerStore in volumes.
Sorry?
CFS allows you to do a similar thing
to VerStore, yeah. Sparse CVOs.
By over-provisioning.
Yeah, sparse CVOs. Yeah.
It's nice for iSCSI.
Yeah. Oh, yeah. Sunday on Linux LVM is supported, and there are even more. Some utilities to go with it. There's a super utility called Geom that can do most everything to every class, but every class also has a little module that is installed in user land to do the specifics of that class. And if you invoke Geom as gmirror, it knows to work with the mirror module. You can also say Geom mirror label to create new mirror. GStat is a utility to do statistics on Geom providers, like number of blocks per second, number of writes per second, and so on. Geom automatically adds statistics to every layer, so that's very handy. You always can, at every layer in your stack, see what your disk bandwidth is, what your percentage BSD is, and so on. Gpart is a replacement for a program called fdisk, called after the fdisk that was included with Nestos in the past, to create your MBR label. Many operating systems have a command called fdisk, and it works differently in every operating system. If you've used it in DOS, and you've used it in FreeBSD, and you've used it in NetBSD, and you've used it in SCO Unix. It's called fdisk, and it's completely different every time. There used to be a command called GPT in the past to create a GPT partition table. Gpart can do it all. It's a generic means of creating partitions, and when you first create it, you have to tell which scheme you are using. Are you using MBR, are you using GPT, are you using VTOP, or whatever. Getting to the real stuff soon. This is the last slide on the bits and pieces, I think. HAST, high availability storage. It's something put on top of the Geom gate layer, where I can mirror across machines by having one local disk and one remote disk. HAST provides failover. It works together usually with UCART, which is user land address redundancy. So I can make one virtual address for two physical machines. HASD is the daemon, which usually keeps the master and the backup, the two parts of the mirror, in sync. It detects when the master goes away and does a failover to the backup. It can detect split brain situations. Split brain situations occur when both the master and the slave are still functioning, but they don't see each other anymore. So they start a life of their own. It can detect that and make sure that afterwards, when master and slave, or master and backup, can see each other again, they do not assume that they have been running on the master or the slave all the time, but they can detect the split brain situation and not further sync the backup, the master to the backup or otherwise. If it would do that, then it would probably overwrite variable data. Yeah, well, it's part of the whole movement into high availability clustering.
Excuse me, how do you go from there? You have two drives, different?
Okay, on the top it's just a Geom provider again. So you give it a name and it appears in /dev.
Alright, yeah.
And you either put a file system on it or whatever. In the ZFS world, you typically start the master. Well, you don't automatically start ZFS by the operating system. Whenever the state changes, HASD will call a script that you have configured, and you start ZFS in the normal situation on the master machine, and UCART will make sure that your master machine has the virtual IP address. If the master machine goes down, then HASD will detect on the slave machine that it's on its own now, so it can start ZFS. UCART will detect that the IP address, the physical IP address of the master machine is down. It'll take over the virtual address to the backup machine, and because you just started ZFS, and ZFS is always in a stable state when you started it, you just start with a machine again. And then if ZFS is used as an iSCSI provider, or maybe for an NFS file system, whether you want to work in block mode or in file mode, you are just a virtual server in a network with redundancy. Okay.
There's also some documentation for the manual fix where there is no auto fix.
Sorry?
There's also some documentation for the manual fix where there is no auto fix.
Well, this is very difficult, I think,
Yeah.
to document, because it completely depends on what happened in your network.
Yeah.
Why did the split brain occur? And after the split brain, were both, well, obviously both machines were written to, but who wrote to both machines, and what did they write, and is it compatible, or does it conflict?
Yeah.
And I think it's very difficult to make one piece of documentation that covers all cases. So. But that's why KLM and then other airlines still have pilots in the cockpit. They have so many machines, but there are circumstances where you need a human intervention. People who can think and do some reasoning, and not everything can be put into equipment and procedures and programs. And I think that's the same for the split brain situation. BSD installers, most of it was covered in the previous talk already, so you can skip sys install and BSD install. There's one more BSD installer. Some company in America took over the PCBSD project some time ago. PCBSD is in fact FreeBSD, but wrapped in such a way that it's relatively easy to install for less experienced people, and it is a complete desktop operating system, including a GUI and all the applications you want. It all works nice together. The guy who's maintaining PCBSD at the moment wrote a new installer for PCBSD a couple of years ago, and it's in a similar spirit to the BSD install, but it's a bit different. And he recently added a feature that from a PCBSD DVD or CD-ROM, you can install a full PCBSD on your desktop or laptop, or you can just do a plain FreeBSD install without ports if you want to create a server. So you can use that to install plain FreeBSD as well. By the way, I have some swag put on the table outside, some CD-ROMs or DVDs with FreeBSD and PCBSD, both 32-bit versions and 64-bit. Take them if you want to. They're there. And the reason I tell you about the PCBSD installer is because BSD install is much better than sys install. It can do GPT, for instance, but it still doesn't know about CFS and some other stuff. That will come in time, but both are developed in parallel, independently from each other, and PCBSD can do some stuff that BSD install cannot yet, like CFS. Right. I've given you all the ingredients, or most of them, and you must be a bit dizzy already. Now you have to put all this knowledge into use. You have to plan the installation of your FreeBSD machine. So, things to consider. Do you have multiple disks, and do you want some kind of mirroring or other redundancy, wait 5, AZ or whatever. Do you want multiple operating systems? Is this your laptop and you occasionally have to boot something like Linux or even worse? Then you best use MBR partitioning with a boot 0, so you get a nice boot menu. You decide on what file systems to use. UFS or UFS version 2, which has large address space, some organized features. Your machine, if it's an embedded or a small machine, use UFS. We just discussed that CFS is both hungry on memory and address space. If it's a big server, make it CFS only. UFS, CFS hybrids can also exist. You can do part of the file systems on UFS, part on CFS. There was a time when we could not boot from ZFS, as you asked, and in that time we put the root file system, maybe root plus USR and var on the UFS disk and the remaining part of the machine on ZFS. You have to be careful. ZFS was developed on Solaris and is written to work together, to work nicely together with the Solaris virtual memory model. The FreeBSD virtual memory model and Solaris virtual memory model are not the same, and this means that kernel memory allocation in ZFS is different from kernel memory allocation under UFS. And you can easily create memory starvation, a lack of virtual memory on a machine if you use UFS and ZFS together. There are some uses where it can be done. I told you about a talk I did before, putting NanoBSD below ZFS and NanoBSD still using UFS, but I'm talking about a very small file system, so everything takes up less than a gigabyte or half a gigabyte. And, that can survive quite well, but if you want bigger file systems or memory intensive file systems, I/O intensive file systems on UFS on a machine that also has CFS, then you have to do some serious tuning and make sure they don't starve the machine and, well, in fact, hang your machine. This cannot be cured easily because of the CDDL license. It's very difficult to change CFS to use the FreeBSD VM system because of the license, and to change FreeBSD to use the Solaris VM system effectively would mean that most of the kernel gets replaced by the Open Solaris kernel. If you want that, you just get some Open Solaris from somewhere, Open India, and install that. So yeah, ZFS is very, very nice for servers, but it has a few drawbacks. It's very nice. It's not difficult to live with it. I've done that for a couple of years now and get used to it. It's no problem, but you have to be aware. Well, your partitioning, if your disks are bigger than 2 terabytes, you have to go for GPT because MBR just doesn't do it anymore.
Or if you want to try once.
Sorry?
Or if you want to use the try once.
If you want to use the try once, yeah, not a good reason. If you want, well, if there's also a legacy operating system on your machine, you have to go for an MBR because legacy operating systems don't understand GPT. Like old versions of, you name your favorite operating system. Who said that 9? Your swap space. Yeah. CFS has the concept of a ZVOL, a kind of a block device which in turn is treated as a file. And early documentation also, well, you use a ZVOL for your swap, and there's even a property you can set that under FreeBSD it's automatically recognized as a swap space during startup and added as a swap space. Don't go that way. and the heavy load, ZFS needs some more memory to do swapping. And I still have a couple of machines that have been installed more than 2 years ago, where swap is on a ZVol, and I still have to go to those machines to make a backup of everything on ZFS and create a smaller pool so that they can have separate swap space. Unfortunately, that's the disadvantage of being one of the first to use it. But a swap in a ZFS ZVol under FreeBSD doesn't work. At least at the moment.
Just a stupid question. This can't be solved by just extending the swap space by adding more volumes and...
No, it needs some memory while it wants to write to the swap. So ZFS will allocate memory in the process of swapping.
Yeah. Okay.
So your swap is usually on a separate partition, either in a BSD label or directly on an MBR partition. I wouldn't do that, but it can be done. Linux does it. Or on a GPT partition, that's most likely in this case. Mirror your swap. Why? It's only transient data. Well, it's so lovely to have that machine in the data center across the world panicking because on read of your swap data it gets a disk error. I have so many sysadmins tell me, why do you mirror your swap? It's not necessary. Okay, now you know why. So, your typical laptop or your desktop usually has one disk, or often has one disk. You install an MBR slice map and boot 0, so you get a boot manager. Use one slice for FreeBSD. If you only want FreeBSD, make the slice cover the whole disk. If you want other operating systems, make it a bit smaller and use some space for other operating systems. Inside the FreeBSD partition, use the BSD label, create your slash or swap, your temp file, user home, whatever file systems you want. Everything can be done using both the old sysinstall or the new BSD install. You can use the other slices for other versions of FreeBSD. I've got machines, I've got a test machine at home where I've got FreeBSD versions, 4 FreeBSD versions on it. I've got version 8 in 32-bit mode, version 8 in 64-bit mode, version 9 in 32-bit mode, and version 9 in 64-bit mode. And I can boot it using either of the 4, whatever I want to use for testing. Or you can even, if you're brave, put another operating system in one of your nodes. Try over Solaris, it's nice, or try NetBSD. A server, 2 disks, and you want to go for UFS. Maybe it's an older server, not too much memory, or only 32-bit mode. Well, I would say use GeoMirror to mirror your physical disks. The picture I've shown you before. Unlike the picture, put an MBR on it first and put BSD label on top of the MBR. And use boot 0 if you want. You can also use MBR if there's just one version. By the way, before the well, not only before. What I often do on servers is I take the first gigabyte of my hard disks and I put a minimal FreeBSD install in the first disk. And on this minimal BSD install I make one account and I start the SSH. That's very handy. If something happens and I have to repartition or whatever, I can boot it in this first 1 gigabyte FreeBSD. I have something to work with. I don't need a rescue disk or whatever. It's on the hard disk. It's much faster, it's always there, it can't get lost because I lose my disk, or after 3 years of not being used, the lenses in my CD-ROM player are unclear and it can't read the CD-ROM anymore. I've come across all that. In the old floppy days, you haven't used the floppy drive for a year or two, you put a floppy in, you hear a lot of noise, you take your floppy out, it's completely torn apart because of the dust sitting on your the head of the floppy drive. Put a small part of your hard disk apart, put a minimal FreeBSD on it, saves you a lot of hassle. And in that case, boot zero is your friend. Well, most of it can be done using sysinstall and using BSD install, except for the GM part. There are some recipes on the internet, they're very easy to find. The trick is you can do 2 ways. You can install FreeBSD first and create a mirror later. The trick there is don't use the last block of the disk. So while partitioning, make your last partition 1 sector smaller and leave the last sector for the mirror to use. Then when your machine is installed, preferably with the 1 gigabyte rescue FreeBSD in default. What you then do is you create a mirror of the other partition that holds your FreeBSD that you just installed. You create a mirror with just 1 disk, the first one that you've installed. Then later you insert the second disk into the mirror. And when you insert the second disk into a single disk mirror with GM, it automatically starts replicating from the first to the second disk, and it shows you, if you call for the status, how far it is, and when it's done, you've got a mirrored system. Works very nicely. The other way around is start your installation disk and go into shell mode and do the wall setup manually. Create your mirror, create your NVR, create your BSD label, everything from the shell, and then install into that. It's not that difficult. If you go into the distribution directory on the DVD, it's divided into base and games and manual pages and documents, so all of the parts of the distribution, and every subdirectory has an install.sh, and just call it, it installs that part for you. It's not that difficult, it's some extra work, and I hope in the near future BSD install will do all that for you automatically, and you can just say, well, I've got 2 physical disks, I want to mirror them first, then put an MBR on it, and then put a BSD label on it, or the other way around. Is there a pen here? Yeah. The other way around. 2 disks. First 1 gig, I put a rescue FreeBSD. Another one here, independent from each other. So if the disk crashes, I can still move from that one. Then I create a mirror of these 2 slices, mirror them together, and then put a label on it. So the production FreeBSD is mirrored, but my rescue part is still unmirrored. And that's the nice thing about Geom. You can order the layers whatever suits your need. You can put mirror below, so the whole disk is mirrored, and then put an MBR on it to make slices out of it, or do it the other way around, put an MBR first and put the mirror inside the MBR.
But this works with MBR? That works with GPT?
This works with MBR. Yeah, well, it's a good question. GPT is a bad kid on the block.
Yeah, because it uses the last block.
No, because every class that uses the last block for data, for metadata, as a provider, provides something that is 1 block smaller. So you never override the last block of your lower layer.
Right. Yeah, okay.
That's not a problem. The only problem with GPT, may be that the geom_par GPT class only detects a GPT if it's on a physical disk. I've seen that once, I've not checked that, but that may be an issue. The GPT is not a good citizen if it's not the class which is directly on the hardware.
No, but if you create a mirror on these two disks, so if two disks and you put then the mirror creates in the last sector the geom information.
Yeah.
Now if you put the G part inside this, then the G part will be over there.
Yeah.
The GPT copy of the original table. So if the system boots, it sees the GPT at the beginning, then looks for the GPT at the end and finds the geom. Then what? Because it doesn't know yet about the geom mirror.
There is some issue about the order in which the geom classes are called on tasting. And I don't know exactly how the ordering works, but if I'm correct, then the geom partition tasting is done after mirror tasting. So if mirror finds this first, and let me see. No, if you want to do this with GPT, go back from the beginning. I want the first gig of the disk for my rescue. So in fact I put a GPT on this one and a GPT on this one with two partitions. The first is 1 gig, the other one is the rest. So GPT spans the whole disk in both cases. Then I mirror GPT partition 2 and GPT partition 2 here. That gives me my mirror. And then I have to put a new partitioning layer on top of the mirroring. And that's what I just meant, that GPT is not a good citizen. Well, I tried it once and didn't work. It appears that GPT is not a good citizen on top of other layers. So that means that if I want to do this with GPT, I can use GPT for the division of 1 gigabyte and the remaining part. But inside here I have to use, for instance, BSD label or ZFS. Well, if you use ZFS, you don't need further partitioning. So with ZFS, it's even a little bit different. So this is my rescue minimal FreeBSD. This is another minimal FreeBSD. My swap, do you remember, it's outside CFS. And then the remaining part here is mirrored together, GM0, and I give GM0. No, with CFS I would not even use geom, this is UFS. With CFS I would use CFS itself for mirroring. With UFS GM0 and then put a BSD label on it, and I can make 7 partitions. Yeah. I think that's the way to go.
Yeah, but my systems are too small to run ZFS and too far away from my home to not use the try once option. So I need GPT and I need
so then you would need GPT as the outer partitioner, geomirror inside GPT, so mirror GPT partitions together.
Yeah.
But then you have to, well, the other thing is you could use GPT to create many partitions at the same year, and then make one mirror out of these two, and one mirror out of these two, and one mirror out of these two. That's not a possibility.
Mirror them separately, yeah.
Of course, but
Yeah. Probably better.
There is no one-size-fits-all recipe here, but because of the generic API between the layers of geom, you can do almost every combination, and GPT is done, as far as I know at the moment, the one exception, that it must be at the bottom level and it cannot be at a higher level in the stack. But all the other ones, as far as I know, play very well on top of lower ones. Well, the same server, but then 3 or 5 disks. I would use GM-RAID 3 instead of mirroring. This is quite similar, but still you have to do a lot of manual work, and you cannot just install it on one and then create a mirror. You have to create the RAID set, the RAID 3 before, and then populate it. So it is a little bit more work, but I have machines running like this as well. In fact, I used to have a lot of machines working exactly like this with 3 disks. Two or more disks in ZFS, GPT on the disk. With GPT you have to make one extra partition. It's only very small, like 128 sectors or so, to hold the boot code. It's a separate partition in GPT. It's not a big issue, it's just something you have to know. So you make 3 partitions, boot, swap and ZFS, or 4 if you want the rest with FreeBSD in front. Use the GPT ZFS boot, of course, and create a mirror of the ZFS partition on each pair of disks. So use the Z-pool mirror option. Make ZFS know about the mirroring so it can do fancy stuff. If the mirroring is below ZFS, it will not automatically repair damaged sectors. Hardware, like a little side step, these days, all these hardware vendors, they want to sell you these expensive RAID controllers. And it's very difficult to find hardware that just has plain SATA or SAS ports without RAID and all the fancy stuff at a reasonable price. That's a pity, because I never want to use hardware RAID anymore since I have ZFS. Hardware RAID does not provide me the flexibility of ZFS. It will not auto repair, it will not easily report on what's going on and so. Yeah, some people say don't make one pool with everything in it, make a small pool where your root file system and your minimal operating system lives, and put the rest of it in another pool. There's a lot of talk about it if you follow the threads on the internet. I've done both just as a proof of concept. I've been running machines for a long time with just one ZFS pool with everything in it. So far, no negative experiences, but it's a matter of view more than science. Well, this is the end of the stuff. I think you are a little bit dizzy by now. And I thank you again, many people who helped me do this talk. Some references, interesting manual pages, boot 0 CFG is a tool to configure the boot 0. FDisk and BSD label have been replaced by Gpart, Z-pool and ZFS for management of ZFS. Geo manual pages, make sure you follow the see also links because they point at the various Geo classes that are interesting. Sysinstall and BSD install manual pages, of course. Everything is there in the manual somewhere, and otherwise in the FreeBSD handbook, which I forgot to mention. Questions?
How can we help? How can we help?
Yeah, that question still stands. Well, how can you help? You can help, of course, by testing, reporting issues you find. If you have time and you're brave enough, there are some lists on the internet of project IDs, things that still have to be done in FreeBSD, and you can still join the project. Usually they'll advise you when you ask on the mailing list, start with looking at the problem database, find bugs, and get acquainted with the source by just looking at bugs and trying to find solutions. If you are more experienced as a coder, you can take on bigger projects. Again, no one size fits all. Depends on your interest. Depends on the amount of time you are willing to spend. Depends on the experience you have. There are many ways. And if you're running out of ideas, drop me a line and I'll point you again. Other people have questions.
Just one. A trick I used on Solaris systems is just booting a pen drive containing a ZFS pool, and then creating a slice with just using the entire disk of the system I want to install onto, and just attaching that to the mirror. Just attach the disk to the pen drive, wait for the reset to complete, install bootlock and reboot. Can I do this in FreeBSD as well?
I think you can. I've never tried what happens if you attach a device which is bigger than the existing one, but
That's no problem with
I
ZFS.
think it should work with ZFS, yeah.
It does.
What I would do, that's just because I'm so used to that way of working, is do a ZFS send on one and pipe it into ZFS receive on the other one. But yeah, why not create a mirror and then split the mirror?
Well, I tried this because I had a commercial installer that didn't allow me to create FDisk partitions or use slices for ZFS pools. I just used the entire disk and I had just a few drives in the system and I wanted to have a separate Z pool for data.
Yeah.
So that's why I tried it. It worked perfectly.
Yeah, why not?
Just attach the first, attach the second, and maybe the third, and it just copies them all to the slices.
Nice trick. That's one possibility.
It requires a pretty fast pen drive there. It requires a pretty fast pen drive.
Or a big can of coffee.
Or a good night's sleep, yeah.
Yeah, finally time to see you bed. Another question?
There was one thought I had. There's no circumstance where Geo Mirror, if you mirrored your swap using that, does need additional memory?
No.
Okay, good.
I have made a mistake once on a 3-disk machine to try put swap on a RAID 3, and I don't know if it's because it's not supported, but I had my machine hang several times.
Okay.
After I reduced this to a 3-way mirror, it worked fine.
Okay.
So RAID 3 I wouldn't trust with swap,
Yeah.
but mirroring is okay.
Okay. Yeah. It probably pre-allocates a number of sectors it's going to use for the transfer. Yeah.
Maybe it's the copy on white thing, I don't know. But does FreeBSD allow swapping to files, or you need a partition?
Well, indirectly, if you create a block device out of your file using mdconfig,
okay.
so you change the file into a block device again and then swap to it. On the other hand, ZFS, but it's mostly there just for testing, instead of using a physical disk or any kind of geom provider as a source for a ZFS tool, you can also use plain files as sources. So you can install a machine with ZFS in the kernel or as a module and play with ZFS even if your complete disk is covered by UFS. So on an existing machine, your laptop or whatever with FreeBSD, you just create a couple of files, 1 or 2 gigs each, and you start playing with ZFS. Little side step. Creating a file. Assume I want to have 3 files, plain disk for me, 1 gig each. How would people create a 1 gig file?
Solaris has MK file and DD does as well.
Yeah, DD with a C.
DD will copy 1 gigabyte of zeros onto your file.
Or whatever. Yeah.
I don't need the full gigabyte, I just want to play with it and I maybe use a few megabytes of it afterwards, so why copy a full gigabyte?
No, you can make a sparse file, right?
Yeah?
Is it
How do you easily make a sparse file?
DD with a C? No?
Yeah, that's a possibility. It's a long line, not to remember.
Open
So-
seek to the end.
So few people know that the command truncate
Truncate minus S?
minus S1G file 1, file
Yeah.
2, and so on, does exactly what you want. Create sparse files of 1G. Truncate sets the end of file pointer to whatever value you give it. If the file was longer before, it will truncate the file. If the file was shorter or not existing, it'll just create a sparse file for you.
Yeah.
Okay, so whoever wants to experiment with CFS and redundancy in CFS, maybe test some data corruption, use this.
No, use
Yeah, but
the
this is, I see so many people, even people with years and years of Unix experience, doing all kinds of tricks to create a file to, an empty file to play with as a device. The command has been there for ages in FreeBSD. I never see people say, just truncate it to the size you want. It's so easy.
Then why don't they hard link it to something like a set file size, which would tell people this can be used to set a file size, it's not necessarily a true value.
Yeah, but why is cat called cat and not dog? I mean,
Because
there are some commands in Unix that have a name that does not tell you everything you can do with it.
What, LS? Everybody knows what LS does.
Well, my binary editor is called DD. I do binary patching in files using DD. Echo pipe DD. Works perfectly.
That's why you make snapshots every 5 minutes, do you?
Well, I haven't done the binary editing lately, so maybe since I started using the snapshots, I've never had a need to do that.
Why is DD called DD? No, never heard of that.
There is some history to it. I have read it in the past, but
That's what I call it.
I'm not sure anymore. So I leave it as an exercise to take home, find on the internet what the etymology behind the name DD is.
Misschien moeten we binnenkort gewoon nog een dag afspreken.
Ja,
BSD dag is
ik was net bij mijn op één na laatste slide.
Okay.
So if you have no more questions, I only have one question to you.
Maar de koelkast is ook al op slot, jongens.
Ja.
Oké.
Dankjewel. Dankjewel. The weekend with BSD.
Ja, dat is waarom ik een beetje ook al heb.